So here we are back on lesson 4.3, and now we're going to cover the mean value theorem. What I love about our teacher who wrote this book, Mr. Taylor, he loves to give you a chance to discover something. So here, the mean value theorem, we're going to go through a few examples and see if we can't discover what the mean value theorem is. So he says, draw these lines if possible. We want to draw the secant line between 2 points. We've got our interval from A to B, and so we're going to look at those outputs at A and outputs at B, and then draw those tangent lines that would be parallel to the secant line. Okay, so that's going to be our goal. So first thing is trying to draw those lines. Secant line, oops, not a right angle, my bad. Secant lines from A to B. I would be able to take a slope from that and have an average rate of change. And if I wanted to draw a line that was parallel from A to B, I got that line right there. If I want to draw a line that's parallel, I actually have a tool when I copy and paste. It makes a parallel line. So now all I have to do is just drag it to where I think a tangent would be. And so it looks like it would be right there. Okay. And so let's do this again. And I have my straight line from A to B, and I copy and paste it, and then I'm going to drag it to where I think it would be. And by the way, I see a tangent here and I see another tangent right there. Okay, and then I'm going to draw a straight line from A to B, and here we go. There's my A, there's my B. And I would love to have a tangent somewhere. Oops, that's the wrong one. So copy and paste. And so here, that's my parallel line. But if I try to figure out a place to make a tangent, I'm just not finding a place where, like, I want it to be right there, right? But honestly, that is not the only place that, how do I say this? That's not a specific slope. You know, I'm teetering on the edge. I'm balancing on the edge. So if I drew this, that would also be balancing on the edge. If I drew it like that, it would also be balancing on the edge. If I drew it like that, it would also be balancing on the edge. There's an infinite number of tangents because that's a cusp. And sharp turns, like we know, we can't find a derivative there. So there's no tangent here. Not a single tangent, and that's the defining characteristic of a tangent, is that it's going to touch the curve only in one place, and that there's only one slope for that tangent. So here it's not possible. Okay, so notice then that I have one tangent, I have two tangents. It's this guy and that guy. And here I have no tangents at all. And so I'm wondering, is it obvious then that as long as there's no like cusp right here, I'm able to find a tangent, right? Okay, so let's keep going. And we have these next two examples. And I want to be able to draw a secant across. But notice that if I draw this secant, that I cross the asymptote. And so that would be bad, right? And not only that, but I'm going to copy, I'm going to paste. If I try to find a tangent somewhere, yeah, sure, there's like a tangent here that's the same, but then it also would cross over. So we're going to say, with this one, we're going to say that, again, that it's not really a secant. And not only that, but I'm going to say that there's no tangent, because I can't make sure that it's not going to, that it's the same as the secant, since the secant isn't really real. And again, I'm trying to draw a secant over here, and since there's no point on this line, well, do I draw it here? Do I draw it there? Do I draw it there? Do I draw it there? So again, we have no secant. So we also have no tangent. Okay, because I just don't know where that there is no A. And then here I've got my last one, and I'm feeling better, right? I can actually draw that secant. I wish it was green though. I wish it was green. And when I draw this secant, boom, I feel really good about it. That was very clear. It's even, it looks like horizontal, so that's cool. Copy it, paste it. I'm totally taking it up, copy it, paste it. I'm totally going to drag it up to that spot. And then, hey, wait a minute. What does that spot mean? Like, my function isn't defined there, right? So okay, that's just not possible to draw that tangent. All right, so we had ones where it was easy and we had ones where it was hard. And let's recap. So I just wanted to mention it was easy when there was line that was easy to trace, right? I could just trace it, and I'm hoping now that I am tracing it that it's occurring to you that means that it's continuous. So continuity made it easy. And yet sharp terms made it difficult. And over here we found that they were impossible for various reasons. So now that we've done that, we're feeling like we maybe have like an idea of when we would be able to find that tangent line, right? And so let's take a look at the next 3 examples. It says draw that secant line between the 2 points. And again, we have A and again we have B, and then we're going to check the output at A and check the output at B, and draw all tangent lines that are parallel to the secant line at some point on this interval from 2 to 5. So I'm supposed to be doing green. I'm going to draw my secant line, and there it is. And I'm feeling very good about that. I'm going to copy it. I'm going to paste it. And I believe I could see where that tangent line would be, and it looks like it would be right there. And I'm going to write that down, that I drew a tangent line specifically at this point, which is 3, 1. So he says, estimate the value of C where CF of C is a point of tangency. So C is this point where x equals 3. That's my input value. And my output value is 2. So the point where tangency happens is at 3, 2. Okay. And then let me draw another secant line, and I'm feeling what you're feeling there. It looks like it's kind of off. There's definitely a sharp point, and that bothers me. But if I try to find a slope, I still got one. I could easily find that slope that's tangent. And again, I have another slope that's tangent. Let me try to drag that over there. There's my other slope that's tangent. Oops. And then I want to draw one more, and I'm going to tell you that there's a problem with that one. And the problem is that it's outside of my range, my interval. He says do the interval from 2 to 5, and therefore this line is outside it's outside the interval. So I don't want to use it, okay? But this one, I'm definitely going to use it. It's at 3. And, well, I mean, maybe it's a little bit less than 3. I don't know. Let's say it's like 2.8. Okay. And then I've got another one, and it's right here. And I don't know, let's call it 4.2, because you know how I love 42. And this other one would have been here, and this would have been, 0.5 or whatever. Again, outside of outside of where I'm looking for. All right, so then if I do the next one, here we are, and again, I want it to be in green. And can I get it to draw for me? There is my secant line. And I copy and I paste, and I'm trying to draw a line that's tangent to it. I mean, the tangent. And then I'm going to try and do it again. And then I'm going to try and do it again. Oh, well, shoot, I guess those worked, right? Those two lines, it hit twice. So it hits here, and it hits here, and it hits here, and it hits here. And one or two of them is actually outside of there is my interval, and there is my interval. That's okay, though. All right, so that one I'm not going to use because it's outside the interval. But these are the ones I'm going to use. So here, I'm going to say that's like 2.5. Here, I'm going to say that's like 3.5. And then here, I'm going to say that's like 4.5. Okay? So let's just talk about it off to the side for a moment here. Let's say that I am in space for one moment, and then I'm in space for another moment, and I'm an astronomer. I observe that there is an object here at this time, and then I observe a few moments later that the object is over there. Well, how do I know that the object existed in the moments in between? Well, we have observational evidence that, I saw it over here, and then I saw it over there. So I'm guessing that it probably did exist. And it did definitely make a path from the one point to the other point. How did it flow? Well, I don't know exactly how did it flow. It could have done any one of all of these paths. But I'm guaranteeing you that this blue line, which is the straightest path, that was my rate of change on average. So I know that somewhere in that path, there had to be a moment where I was traveling exactly the same as this blue line. Now, if it was the red line, it would be up here. It'd be right there. It'd be right there. It'd be right there. It'd be right there. It could be a very large number of times. It is finite, though. Okay, it is definitely finite. How many times? I can count them because I have this starting and I have this ending. So it can't be an infinite number of times that I find that secant slope, okay? Here with the green line, there's the secant slope and there's the secant slope. So we're just trying to make sure that you understand that it is possible to say that average rate of change, it's useful. It's very useful to us because there's definitely a moment in time when my function will be going exactly that rate of change. And that's why we're allowed to use averages to decide that something is or is not happening. Okay, so that's the basics. Now, informally, I'll read this for you just because he's putting it in a different way than I just put it. The mean value theorem states that given the right conditions of continuity and differentiability, there will be at least one tangent line that is parallel to the secant line. In more words, yes, let's try this again. The instantaneous rate of change, which is the slope of the tangent, will equal the average rate of change, which is the slope of the secant, at least once. All right, now how about the actual calculus? You listen to me. I appreciate it. Let's actually do it. And by the way, on the mega cheat sheet, this concept is quite difficult. So I give you a very good, here's my cheat sheet. I give you a very good walkthrough of how to do the mean value theorem every single time. Okay, so you just want to pull out the cheat sheet and use it for this entire homework. Okay, so I have it. I am going to paste it on here. Where'd it go? I'm going to paste it on here and we are going to do it, okay? Just exactly like it says. First of all, find the y's. And I know you know this, that I have a tendency to forget that first step. I will often forget to do it. So let's see if I can't do it this time and make sure that I've got it right. F of 3, I'm looking for it. This is 3 minus 6 over 3, which is going to be 3 minus, 6 over 3 is 2. And so that ends up being 1. And F of 6, what is that going to be? It's 3 minus 6 over 6. And that's going to be 3 minus 1, which is 2. And so now I have the y's, yay. And I'm very pleased. And then I have to calculate the slope. Please calculate the slope. So I'm going to say that this is x sub 1, this is y sub 1, this is y, x sub 1 and x sub 2, and y sub 1 and y sub 2. And in fact, some kids like it better when I do it like this, where I plug in the 3 and I get a 1, and where I plug in the 6 and I get a 2. And then they do this as x sub 1, and this is x sub 2, and this is y sub 1, and this is y sub 2. But I'll mention that the formula uses a's and b's. So you can call it x sub 1 and x sub 2 and y sub 1 and y sub 2 because you know the slope formula. Or you can say this is a, this is b, this is f of a, and this is f of b. And if you're following along with the textbook, that's what you're going to see. So it's probably a good idea for you to move to that method. And I honestly feel like if I just looked at a paper and I just saw this with nothing written on it at all, I would still be okay as a grader. I totally know what's happening. But if you really wanted to be precise, it's a good idea to do that up there. Okay. All right. So now here we go. Find that secant slope. So my secant slope is going to be, so this is my secant slope, is going to be 2 minus 1 over 6 minus 3. Oh, and I'll mention that if you want to call it the average rate of change, AROC, you are allowed to. The graders know what that is. All right. They're totally okay with you saying AROC there. So what is that going to end up being? It's going to end up being 1/3. And then here in my formula, I also know that I need to find the derivative. So this function, f of x, is really 3 minus 6 times x to the negative 1 power. And so my derivative, f prime of x, will end up being, the derivative of 3 is 0. There's my negative 6. My power comes down. X gets decreased by yet another number. And so that's my new derivative. Let me simplify that. I'm not going to write down the 0. Negative 6 times negative 1 is positive 6. And that x to the negative 2 drops down in the denominator and becomes positive. So that's going to be my derivative, f prime of x. And it says, find the derivative. So I've done step 1 here. I've done step 2 here. Find the derivative. That's step 3 here. Step 4, I have to set the derivative equal to the slope. So this is step 4, where I say that I have 6 over x squared, and that equals 1/3. Cross multiply to solve, I end up with 1 times x squared equals 6 times 3 is 18. And that 1 is very boring, so I don't need it. So I can take the square root of both sides. And check this out. I end up with x equals positive square root of 18 and negative square root of 18. And I'm happy. Does that mean I'm done? Did I finish? Well, he says find all C which satisfy the mean value theorem on the interval between 3 and 6. So I do need to take a moment and think about that 3 and 6. Where does the square root of 18 fall? If I can't look at a calculator for this, how do I know where the square root of 18 is? Well, let's think about some square roots we do know. Square root of 9 is going to be 3, and square root of 25 is going to be 5. So 18, in fact, let me think about this as the square root of 16. That would be 4. So somewhere between 4 and 5, right? This is approximately between 4 and 5, which means it's definitely in the interval. However, that one is not in the interval. And I'm thinking about this. Why? Because ready? It says, eliminate solutions outside of the interval. So that is step number 5. I just did that. I was thinking about it, and I have now eliminated that. And I'm going to say that my answer, ready, is just this. Now, notice that I'm not going to say that C equals the square root of 18. That's because I'm lazy. If you don't want to be lazy, go ahead and say that C equals the square root of 18. And in fact, if you are looking for multiple choice answers, I hate to tell you this, but you would probably not see the square root of 18. What would you see? Well, the square root of 18 is equal to the square root of 3 times 3 times 2, which means that there's a hidden square root of 9 inside of there, right? Square root of 9 times the square root of 2 is going to be 3 times the square root of 2. So you would probably see that as an answer. And in fact, it might even go all the way and say that C equals 3 times the square root of 2 is your final answer. So it's a tough problem, mean value theorem. We are going to practice it. I guarantee it, a lot. Basically, every single homework for the rest of the school year will have one mean value theorem problem on it. So good luck